Welcome to Crazy Fast Reinforcement Learning tutorial with Cart Poll, Lunar Lander, Car Racing, Pong and Breakout, and Hello World. I'm Super AI from Super AI the God, transforming holistic extraordinary game changer of the decade. It's almost the end of 2024 at the moment I'm preparing this tutorial, and a lot of people is talking right now about these AIs, more or less intelligent. So I think it's a good moment for you to learn more about programming. This tutorial is part of my SuperFast AI and ML 101 tutorial. All the code is on my site, superai.pl. In previous parts I showed you classification, regression, semi-unsupervised learning and simple LLMs. Here we'll talk about reinforcement learning and run examples from the official websites. And in the following one I will tell you more about LLMs and others. If you are new to programming, you could check previous parts, where I show you how you can start working with Anaconda, Jupyter notebooks, etc. So here we go. Have fun. In real-life applications, reinforcement learning is used in robotics to train robots for tasks like object manipulation and autonomous navigation. In healthcare to personalize treatment plans based on patient data. In finance to create adaptive trading strategies. And in self-driving cars to navigate roads and make real-time driving decisions. RL is also applied in supply chain optimization, gaming AI, and even recommendation systems, where agents optimize decisions based on feedback from the environment, in order to maximize a cumulative reward over time. At each step, the agent observes the state of the environment, takes an action, and receives feedback in the form of a reward that helps guide future decisions. RL algorithms can be categorized in various ways, including model-based versus model-free methods, value-based versus policy-based approaches, and discrete versus continuous actions and observations. These algorithms are designed to tackle different environments, such as games, self-driving cars, and financial trading, each requiring specific strategies for optimal performance. Common RL techniques include deep Q networks, DQN, advantage Actor-Critic, A2C, proximal policy optimization, PPO, or a twin delayed DDPG, TD3. These algorithms can be implemented using Stable-Baselines3, which supports various action spaces. All the algorithms are based on the aforementioned key concepts in RL that include the agent, the decision maker, the environment, the system the agent interacts with, the state, the current situation in the environment, the action, choices the agent can make, and the reward, feedback after taking an action, indicating its success. Additionally, frameworks like Gymnasium provide standardized environments to test and develop RL models, making it easier to evaluate and benchmark agents in diverse scenarios. In the context of gaming, RL algorithms are applied to environments like Cart Poll, Lunar Lander, Car Racing, Pong, and Breakout, where agents learn tasks like balancing a pole, landing a spaceship, driving a car, or mastering classic arcade games. These environments are provided by the Gymnasium library, which offers a wide range of pre-built scenarios for training RL agents. For example, in Cart Poll, the agent must balance a pole on a moving cart, while in Lunar Lander, the agent has to land a spacecraft safely. In a car racing environment, an agent must learn to navigate the track efficiently. In Pong and Breakout, RL agents learn to play and compete against themselves or human players. By experimenting with RL algorithms in various Gymnasium environments, developers and researchers can explore the power of RL in different domains, and improve performance across complex, real-world scenarios. We'll test here 4 simple algorithms: A2C, DQN, PPO and TD3, in 5 gaming environments: Cart Poll, Lunar Lander, Car Racing, Pong and Breakout. So at first we'll create Anaconda Stable Baselines environment, with Python 3.10, Gymnasium 0.29, PyTorch 2.2.1, Stable-Baselines3 2.2.1, NumPy 1.25.2, Pandas 2.0.3, CV 24.7.0.72, Matplotlib 3.7.2, and Pygame 2.4.0. As always, you can try other versions, but these are the ones that worked for me. We'll install Gymnasium with classic control games by using pip, but for Box 2D we'll use Conda. For Atari games we'll need to install something called Accept-ROM license. The other libraries will install like before. You can find all the info about it in tutorial at my site. Before we start training our agents, we'll test all the environments. First, in the Cart Poll environment, the agent controls a cart that moves along a frictionless track to balance a pole upright, by applying forces to the left or right, earning a reward of +1 for each time step the pole remains upright. The episode ends if the pole's angle exceeds plus or minus 12 degrees, the cart moves beyond the range of plus or minus 2.4, or if the number of steps exceeds 500. The maximum reward achievable is 500 points for keeping the pole balanced for the entire episode. In this example, we create and run a Cart Poll version 1 environment, where the agent takes random actions, accumulates rewards, and resets the environment after each episode ends. The code initializes the environment, renders it for visual feedback, and collects rewards until the termination conditions are met. Finally, the code prints the total rewards for each episode and the mean reward across all episodes. You can read more about this environment on the Gymnasium's website. Next we have the Lunar Lander environment. Here the agent controls a spacecraft to safely land on a designated pad, earning rewards for successful landings and incurring penalties for crashing or running out of fuel. The episode ends if the lander crashes, moves outside the viewport, or becomes inactive. The maximum reward achievable is 200 points for successfully landing and coming to rest. In this example we create and run a Lunar Lander version 2 environment, where the agent takes random actions, accumulates rewards, and resets the environment after each episode ends, ultimately printing the total rewards for each episode and the mean reward across all episodes. In the car racing environment, the agent controls a rear-wheel drive car in a top-down racing scenario, where the track is randomly generated for each episode. The agent earns a reward of -0.1 for every frame and an additional +1000 divided by n, for each track tile visited, where n is the total number of tiles. The episode concludes when all track tiles have been visited, or if the car goes off the track, resulting in a -100 penalty. The maximum reward achievable depends on the number of tiles visited, and the agent's performance in staying on the track. In this example, we create and run a car racing V2 environment with domain randomization enabled, which allows for varied backgrounds and track colors. The agent takes random actions, accumulates rewards, and resets the environment after each episode ends. The code initializes the environment, renders it for visual feedback, and collects rewards over 500 steps, ultimately printing the total score achieved by the agent. And now we have two Atari environments where, at first, our agent plays Pong, and unfortunately loses badly. And finally we have the Breakout environment, where we'll try to teach the agent to hit as many bricks as possible. And as previously mentioned, you can read more about these on the Gymnasium's website. So, let's teach our agents how to land, drive, play Atari games, and at first let me check if we are using our GPU, because here it might help us a lot. I'm using here RTX 4080, so it's not the fastest card, but is good enough. If you're using better card, the training time should be shorter. And okay, I have it on. So the first algorithm we'll be using is Advantage Actor-Critic, A2C. You can read about it on the linked sites. It is particularly effective in the cart pole environment, in which the objective is to keep the pole balanced upright, by applying forces to the cart either left or right. A2C is a synchronous, deterministic variant of the popular asynchronous Advantage Actor-Critic algorithm, A3C. It employs two neural networks. The actor, which decides which action to take based on the current state, and the critic, which evaluates the action taken by estimating the value of the state using the advantage function. The advantage function calculates how much better, or worse, an action performed compared to the expected outcome, guiding the actor to refine its policy, by iteratively updating both networks during training, and running multiple instances of the environment in parallel. A2C can efficiently learn to balance the pole for extended periods, achieving high scores in the cart pole environment. And the best thing is, just like with other algorithms, you don't need to completely understand it to make it run. You can simply start with an example from the library site. So, let's restart the kernel and check if we have all the libraries we need. I do, and if you don't, you can install them with these cells. And finally, we initialize the cart pole environment. We define the A2C model. We then evaluate the performance of the untrained model, and train it for 10,000 time steps. Next, we train the model for 1 million steps. You'll see the performance go up and down. At first, the model solves the environment by earning 500 points, but then it fluctuates due to exploration and overfitting. By tracking the average reward over time, we can understand these changes better. To avoid overfitting, we might use techniques like early stopping or adjust hyperparameters. If you want, you can try using this model on your own, and make changes to see how they affect the learning process. And now, let's move on to the next model. Deep Q Network, DQN. Deep Q networks extend Q learning, so first let me tell you about Q learning. Q learning is a model-free reinforcement learning algorithm that helps an agent learn the value of taking specific actions in different states to maximize cumulative rewards over time. The algorithm updates a Q value table for each state action pair based on the Bellman equation, improving decision-making through trial and error by balancing exploration and exploitation. Q learning is effective in environments with small discrete state spaces, where the agent can easily store and update Q values in a table. However, in complex environments with large or continuous state spaces, like video games, Q learning struggles due to memory and computational limitations. Deep Q networks extend Q learning by using a deep neural network to approximate the Q values, enabling the agent to scale to more complex environments. The neural network takes the current state as input and outputs Q values for each possible action, allowing the agent to select the best action. For example, in the Lunar Lander environment, we have a scenario where the agent controls a lunar lander and learns to safely land on a platform. That's cool, isn't it? And like previously, you don't have to know exactly how to implement DQN from scratch. You can start with the example from stable baselines and continue from there. But it's good to at least learn about environment, rewards and actions the agent can take. Here, the agent can take 4 actions: doing nothing, firing the left orientation thruster, firing the right orientation thruster, or firing the main engine to control the lander's movement and safely land it on a platform. The agent stores experiences in a replay buffer, and updates its Q values using batches from the buffer, with a target network to stabilize training. After sufficient training, the agent learns to navigate the lander effectively, and its performance is evaluated through average rewards, and visualized by rendering the environment. So let's try train the agent from this example with DQN. We'll use here the same environment we used with the cart pole, so the necessary libraries should already be installed. However, it's good to verify this and install any missing ones. Since I have everything set up, I can move on to our example. At first, we create the Lunar Lander environment, and instantiate a DQN agent with a multi-layer perceptron policy. We save the model as DQN Lunar, and reload it for evaluation. We evaluate the agent's performance over 10 episodes, assessing the mean and standard deviation of the rewards. And finally, we run the trained agent in the environment to visualize its actions, comparing its performance with the untrained model. And as you can see, we probably shouldn't trust this agent with the real lander. So next we train it for 200,000 time steps, and monitor the training logs. While the agent's performance has improved, it still is not the best pilot. Similar to the pole balancing task, the agent's performance fluctuated during training, sometimes improving, sometimes regressing, but overall progressing. This fluctuation is normal as the agent fine-tunes its strategy through trial and error. And finally, we train our agent for 1 million time steps. Unfortunately, it wasn't enough to create Han Solo, but it has potential and has definitely improved. So, now, if you want, you can improve it. To do it, experiment with hyperparameter tuning, and use callbacks like evil callback or checkpoint callback for periodic model saving, and performance monitoring. Leverage logging tools like TensorBoard for visual insights into training metrics, and increase evaluation episodes for more accurate assessments. Additionally, handle the dunce flag properly, use environment wrappers for normalization, and add visualization tools to analyze the agent's behavior and progress. So, our third RL algorithm is Proximal Policy Optimization (PPO). We'll use it with cart pole environment and car racing. PPO is a popular reinforcement learning algorithm introduced by John Schulman and his team in 2017. It is designed to make learning more stable and efficient, while balancing the need for exploration and exploitation. PPO works by making small controlled updates to the policy, which helps prevent large changes that could destabilize training. This is done through a so-called clipped objective function, which limits how much the policy can change in one update. PPO is simpler and more efficient than an earlier algorithm called Trust Region Policy Optimization, TRPO, which had a more complex process to ensure stability. If you want, you can read more about it for a deeper understanding. However, for the purpose of this tutorial, all you need to know is that you can easily use it with stable baselines. So let's see how to use PPO with stable baselines, starting with the classic kart pole task, and then moving on to the car racing environment. The car racing environment is a continuous control task, where the agent must navigate a car around a track, making it significantly more complex than kart pole. It requires the agent to learn not only how to accelerate and brake but also how to steer effectively, providing a rich setting for testing advanced reinforcement learning algorithms like PPO. But before we let the agent drive, let's try the kart pole. As previously, let's check if we have all we need, and let's paste the example we'll use to learn. In here, we set up the environment using the PPO, leveraging 4 CPU cores for parallel processing. By utilizing subproc vec NV, we create multiple instances of the kart pole environment, enabling the agent to learn from diverse experiences simultaneously. This parallelization speeds up training and helps stabilize learning by exposing the agent to a wider variety of states and actions. If we don't have 4 CPUs, we can reduce the num CPU variable to a smaller number or use dummy vec env, which runs all environments in the same process but may be slower. We can see how the agent handles the situation without training, and after 24,000 time steps, and it's quite good. If you want, you can also try training for 1 million time steps to achieve the maximum reward. And meanwhile, let's check it with the car race. We'll see here totally untrained agent, as well as agents trained for 1, 2, and even 5 million time steps. Do you think there will be any difference? Let's find out. After restarting the kernel, we check if everything we need is still there. And we check how the agent performs without any training, as it starts with random waits after the kernel restart. And as you can see, it's neither fast nor furious yet. After some training, it gets better. Just be advised that it's X times faster here due to my editing. During the training of our PPO agent, you can observe the car's progress in real time as it navigates the track, with the render mode set to human, while the car is visible and its movement is displayed. The rendering may not be as smooth due to the computational load of training. This visual feedback allows us to observe the agent's performance and behavior, helping us understand how well it is learning to control the car and adapt to various racing conditions. You will see in a moment why it can be helpful. After training, we can save the model for future, reload it and see the trained agent driving. Now, after loading the model trained for 10,000 steps, we continue its training for 1 million additional steps. This time, however, the render mode is not enabled, meaning there will be no visual output during the training process. This approach helps to save computational resources and speed up the training, allowing the agent to focus solely on learning from its experiences in the environment. By reducing computational overhead, it enhances training efficiency. When we get our trained agent, we can of course save it, and after loading it, we can observe how it performs. And as you can see here, I've stored this saved agent on my website. So, at the moment I'm uploading this tutorial. Everyone can download it and test it without having to train the model themselves. And here is our agent in action. I would say, fast, kind of, and definitely furious. Well, okay, so this time, let me show you an agent I trained for 2 million time steps in another notebook. It's also online, so if it's 2024 you can probably download it. And if you were watching it a bit later, well, who knows? And here it is, but I think it's asleep or something. Okay, so now, without further ado, also ready to be downloaded from my site. A 5 million time step learner, fast and furious. Just, that wasn't the task, or was it? So, after 2 days of training this agent, I wouldn't call it either Dom Toretto or Letty Ortiz, and I'm not yet ready to give up. Not yet. Not yet. No. Okay, this one looks promising. Well. So, it could be better, but for this tutorial, that's enough. You can find all of this and more on my website. The last model I trained for around 400,000 time steps. And I would say it's performing better than the agent trained for 5 million steps. With this best model, I stopped the training every 50,000 steps. If it started to behave erratically, I discarded it. And if it performed well, I allowed it to train longer while monitoring its progress. But of course, there are better ways to achieve excellence with PPO. The provided code could be improved by organizing it into functions for better readability and modularity, additionally increasing the number of evaluation episodes, implementing error handling, and formatting the output for clarity could enhance the code's robustness. Key hyperparameters, such as the learning rate, entropy coefficient, and batch size, could be adjusted dynamically to improve exploration and convergence stability. Early stopping could save computational resources by halting training when performance plateaus. While learning rate schedules, for example, annealing or decay, could prevent overshooting optimal solutions. Finally, curriculum learning could help by gradually increasing track complexity, improving training efficiency and performance over time. So, now we can move on to the next algorithm. Twin Delayed Deep Deterministic Policy Gradient, TD3, and we'll use it in the Lunar Lander continuous environment. Like before, we'll use the example from the Stable-Baselines site, but just to be aware of what we are using. TD3 was developed by Scott Fujimoto and his colleagues in 2018, specifically designed for continuous action spaces. Building on the earlier DDPG algorithm, TD3 introduces several enhancements to stabilize learning, including the use of twin Q networks to reduce overestimation bias in Q value estimates. It also employs delayed updates for the policy and target networks, which helps prevent oscillations in the value function. Additionally, TD3 incorporates target policy smoothing by adding noise to the target policy during updates to improve robustness. In the Lunar Lander continuous environment, TD3 trains an agent to control a spacecraft's landing by adjusting continuous variables, like thrust and rotation, allowing for more precise control compared to discrete action algorithms. Okay, so let's see it in action in our stable baselines environment. At first, as always, we check if we have everything we need. Next, we check if the pasted example works. And finally, we train it for 25,000 time steps at first. And check how it works, and I would say, not bad for starters. So we can train it for 1 million time steps now. After that, we can see that the actor and critic losses show some progress. However, it seems the agent may still need more training to fully solve the environment. Nevertheless, we will leave it at that. If you want, you can train your Han Solo further at home, and then test like here with the chosen model. May the force be with you. And now, let's move on to our final examples of reinforcement learning. This time, we'll use advanced Actor-Critic, A2C, once again, but with Atari environments, Pong and Breakout. So, just a basic check to see if everything works. Now, let's see the untrained agent. And yes, you can probably guess which one it is. There is a lot of work ahead of us. So let's start with a 25,000 time steps warm-up. And as you can see, we made some progress, but that's just a beginning. Let's add 1 million time steps to our training. This should make us much better. You can download it from my site. And here we go. Now, not what I hoped for. So let's do some extra learning for 10 million time steps. This should be enough, don't you think? Unfortunately, as always, our skills fluctuate. We get better, we get worse, but overall, we are still much better. So, I'm saving this one for you, and if you want you can download it. And who is the master now? We are, yes. Okay, I thought about training one more agent, with less than 10 million time steps but decided not to do it. If you want, you can try here, and stop when you'll notice that your agent reaches the maximum. And you can test all your agents one after another like here. Oh, and to improve the agent's learning, you could increase the number of parallel environments, NENVS, to A+, adjust key hyperparameters like learning rate and entropy coefficient, and extend training to, for example, 20 million time steps. You could implement reward shaping, use a learning rate schedule, and experiment with data augmentation techniques like frame stacking and random frame skipping. Additionally, you could regularize the model with dropout, apply advanced exploration strategies like epsilon greedy with decay, and monitor training with tools like TensorBoard to track progress and enhance generalization. And that's all about Pong. Good luck with your own tests, and let's move on to Breakout. So, we restart the kernel and check if everything is still okay. We visualize how the agent plays. In the Breakout environment, the agent's task is to control a paddle at the bottom of the screen to bounce a ball, and break bricks arranged at the top, with the goal of clearing all bricks without losing the ball. The agent achieves this by using reinforcement learning to predict the ball's trajectory, moving the paddle accordingly, and optimizing its strategy over time to maximize rewards for hitting bricks and avoiding life loss. And now we do the warm-up training with 25,000 time steps. And as you can see, there isn't much progress yet. So now let me train our agent for 1 million time steps. This should make a difference. You will have it ready to download if you want on my site. And here we go. Now, that's what I'm talking about. So, we are going in the right direction. Let's then move on to the 10 million time steps training. Do you think we'll see a difference then? And ta-da, that's something. I'm impressed. And you can achieve all of this without needing too much knowledge about the algorithm you're using. Awesome. And of course you can download this trained algorithm from my site, so you don't have to train yours from scratch. And by testing different models one after another, you can clearly observe the effects of learning in real time. This will allow you to compare how each model performs, and identify which configurations lead to better results. Oh, and as always, to improve your agent's training, you can increase the number of parallel environments, tune hyperparameters like learning rate and gamma, extend training, and incorporate reward shaping and exploration strategies to enhance learning and generalization. Tools like TensorBoard could also help refine training and boost performance. And that's it for now from me. In the next part, we'll talk about LLMs. I hope you enjoyed this tutorial and learned something new about reinforcement learning. With the tools and knowledge you've gained, you can now continue improving these agents at home and tackle more complex challenges. Feel free to modify the examples, experiment with other RL techniques, or try different tasks. If you'd like to dive deeper into these methods, visit the sites with the examples we've used here. With each change you make, you'll deepen your understanding of the topic. So, good luck, and have fun. Meanwhile, the next major focus in AI and ML is LLMs, LMMs, and AGI, which we will explore next. But for now, let's take a break. And thanks for watching this. You will find the next part of this tutorial on my YouTube channel. And if you want to get notifications about the newest videos I make, hit that subscribe button. Once again, thanks for watching, and remember, improve yourself, improve your business, improve the world, but also live and have fun. Yours, Super AI.